Hi, my name is Vinay, and in this balancing board series of experiment we will see how we can use a PID controller for the velocity control of the DC motor. So this is the same mechanical setup description in 20sim as the previous experiment. So here we are using a velocity actuator to represent a DC motor, followed with a spring damper, friction, gearbox, bearing and inertia model. So this inertia model represents the wheel, this is the bearing of the motor, which is the gearbox, so which is set to 4.6, which is as per the data sheet of the motor. The feedback is taken and converted to 129 counts per revolution and given to this subcontroller. So here this time we have used a PID controller instead of PI as in the last experiment. So PID control will give more accurate velocity control of the DC motor. You can have a damping coefficient and you can see the effect of damping coefficient on the control of the DC motor. The counts are given from this input and converted to revolution by this block by dividing with the value of 129. Okay, and this block converts this revolution counts into velocity feedback. This is in turn given to this plus minus block. Okay, so this plus minus block converts the input from the motion profile and subtraction of this input velocity feedback into error. The error is given to a PID controller, which in turn decide how much output should be produced to the DC motor to control the velocity. There is a signal limiter in between, so that makes sure that the output remains in the range of plus minus 1, else the motor may go in saturation. There is also a feed forward block with a small value, so that is just to adjust the velocity feedback to the output. So this is the signal monitor that we need to observe and see how it works. So let's simulate this. So this is how it works and this is how it's performing. You can always adjust the PID controller values to see how well or best they can perform. For example, if I make it to 0.03 and you can see the difference, a slight difference is there. Okay. So let's download this. You can go to Tool, Real-Time Toolbox, C code generation, select that 4C template and the sub model as this PID controller. In the 4C toolchain, you can select the balancing board template and click OK. You have to make sure the board is powered on and connected through a LAN cable. Go to connect block. The input is coming from the encoder of the right motor. To select the right motor quadrature counter, and these are the two outputs, the right motor to right and left motor we are just connecting to the static value of 0 so that it do not moves randomly, and compile it. We go to command block. It runs for around 6 seconds with a step frequency of 1000 Hz. You can change it to 500 if you wish. So we will run with the logging. So we can select the variables from here. We can select the velocity feedback signal monitor, the plot, log it, and the motion profile velocity output. This is also we will log it. Just click apply and we will just open the camera to see the velocity bar, the balancing bar, and see the velocity plot in it. Okay. So we just run with logging. So here you can see, so the motor rotates, it rotates and stops back. So here you can see this guy is also following the same plot as in our simulation profile. Okay, with a slight delay and oscillations on the top and bottom. Okay, so you can always change the PID controller values and see the effect on that. For example, I make it 0.01. So there will be a delayed start. But less of oscillations. Yeah, so here you can see that if you reduce the KP, there will be delayed start. Okay. If you increase the KP gain too much, then there will be higher oscillations. For example, if you make the KP as 0.1, so there might be oscillations and jerks coming at the output side. So that's too much of oscillations. So there you can see that this is how it performs. I stopped the model to bring any damage to the system. So I make it KP as 0.0001 again and see it again. Okay, so there it plots again. Okay, so that was velocity control using PID controller. This will be the end of the experiment. Thank you.